there's no Sarbanes-Oxley
But what did
Okay, well, good afternoon. Welcome to Principles of Oceanography.
Okay.
The week when we're discussing atmospheric circulation. And as they said in the announcement that I sent out before class, what I want to do today is to briefly finish off some of the material that we covered in Tuesday's lecture. There's a couple of topics that I didn't quite get to, and I'll just sort of recapitulate what the chapter gives us an overview of. And then I'm going to have everybody, all the teams, separate into the breakout rooms. And I'd like, for the balance of the class, for the teams to consider what they need to do to complete the milestone 2 assignment. And specifically, one thing that I'd like the teams to consider is how we apply the principles of oceanography that we're studying in this class, that we're covering in the readings, that I'm trying to tell you about in the lecture material, and that you're encountering as you begin to do research. How do these principles apply to your research topic? I want you to make direct connections between the things that we're learning about and what you see and what you learn in the process of doing your research project. And that's how, as an aside, that's how we really learn things. We read them in books, we hear lectures about them, and then we find ways of applying them to more specific examples. And that process of applying theoretical concepts or concepts that we read about in books to more specific examples really cements the connections that we make between principles. So that's what I want you to pay attention to as we go forward. And just as a review, what we've covered so far has been sort of the human dependence and perception of the ocean. We talked about exploration, resources, management, how ocean science is conducted. Then we looked at ocean basins. We looked at the oceans as they exist on the planet today and how these ocean basins came into being. Specifically, we looked at plate tectonics, this paradigm shifting masterful theory that explains how Earth's history has preconditioned the positions of continents and oceans. We learned about ocean zones, the geologic history of oceans as is written in the sedimentary record. Ocean properties and ocean structure based on how the ocean, the properties of water, its dissolved solids, its temperature, give rise to stratification. And this stratification directly applies to weather and climate. We thought about ocean chemistry We looked specifically at the dissolved solids in ocean and considered the major components of these. Dissolved gases, the way in which the interaction between the ocean and the atmosphere provides oxygen, both for that we breathe and that marine organisms can use. And then we looked in particular at CO2 and its importance in ocean chemistry, specifically the relationship between CO2 and alkalinity, or the acidity of the ocean. We're now considering atmospheric circulation. We're taking the properties of heating, and we're introduced to the concept of the Coriolis effect, and we're looking at weather, climate, storms, etc. Next week, we'll be considering ocean circulation in much the same way. And many of the principles that we learned about in this week's material will be applied to a different fluid body, namely the fluids in the ocean. What's to come are taking these concepts of ocean, the physical oceanography, the chemical and geological oceanography, and then looking at how the living components of the ocean, the plankton, the marine communities and marine ecology, how they function within this environment. And finally, we'll be looking at ocean resources, fisheries, energy, the way in which human activities have led to pollution of the ocean. So these are some of the major principles. Not all, and I'm not intending this to be an exhaustive list, but what you should have in the back of your mind as you're going through this. All right, so just to recapitulate what we talked about in today's, any questions about that before I go on? Any questions about trying to understand this? So in our breakout rooms, when we break up the teams when I finish in about 10 minutes or so, we're going to be looking at each team should be considering their milestone 2 project, what they have to do to complete that. Carrie and I will be going from room to room, breakout room to breakout room, and conferring for 5 to 10 minutes with each of the teams to try to give you some advice. And then you can use the balance of time during the class to do research, go to the Web of Science, start formulating the different written components of the milestone 2, and we'll go forward that way. So questions about that before I go forward? Any questions? No. Can I ask you to do something, if you would, for me, please? Would you turn on your cameras? Because I find it difficult to, without any feedback, to have a sense that I'm keeping your interest and your attention, or that I'm losing things. So
sure, Professor.
Yes, Amanda, please.
Oh, sorry.
Was there a question?
No, I was just like, yeah, I'll turn on my camera.
Okay, great. So go ahead. All right, yeah, thanks. And I don't know if it's going to hurt our bandwidth or how that'll work, but it'll help me a little bit to, to be able to see people reacting. And, if you want to wave your hands or whatever, that's great too. Okay, so the key concept is this uneven heating of the atmosphere. The atmosphere is heated by energy coming from the sun. We talked about that. And this heating through the process of convection, it creates local warmer patches of air, which are less dense and are displaced upward by more dense air. So there's constant motion of the atmosphere over vast scales set in play by this differential heating, that the planet is heated more efficiently at the equator, and the air starts moving. The Coriolis effect adds a twist to all this motion, so that anything moving in the northern hemisphere is deflected to the right by the Coriolis effect, and anything moving in the southern hemisphere is deflected to the left. And this motion, this deflection to the right or the left, applies regardless of direction. If you're moving to the east or the south or the north, in any direction, the Coriolis effect applies. And the other key component of the Coriolis effect is that it is greatest in high latitudes and goes towards 0 as you approach the geographic equator. And the combination of all these basic effects produces patterns of weather and climate, which are chaotic at small time scales. In other words, we can't reliably predict the weather more than a week or so in advance, but we can make generalized predictions about what the weather is going to be like generally on average at different seasons of the year and under different circumstances. Okay, so this is the key processes. We left off last week, so this is the concept of uneven solar heating, that the excess energy, the excess heat at the equator is transferred polewise, and the transfer of heat results from movement of water, and specifically movement of water as water vapor in the atmosphere or as ocean water in ocean currents, and that's what we'll be looking at next week. So moving masses of air and ocean currents transfer energy from the low latitudes towards the high latitudes, key component there. And that this process produces convection cells, and we've identified a number of important convection cells. The Hadley cells are those that are on either side of the equator, that there's a convergence zone, the intertropical convergence zone near the equator, not the geographic equator, but the temperature, the seasonal equator. Okay? And so broadly speaking, we can expect alternate regions of high and low pressure with increasing atmosphere. So Hadley cells nearest the pole, Ferrel cells in the temperate regions, and then polar cells in the Arctic and Antarctic areas. Okay, so those are the motion of the Earth, and then the Coriolis effect is deflecting that motion to the right in the northern hemisphere. So air moving to the south in the northern hemisphere is deflected westward. Air moving north in the southern hemisphere is deflected westward as well. So this westward deflection turns out to be really important. We're going to see that again when we look at ocean circulation patterns. So there's a general westward deflection of motion around the equator. It's westward intensification. And it's going to turn out that this westward intensification plays a big role in the way in which ocean currents are shaped. Okay. Some other important factors here are that there are clouds and precipitation and weather. Suspended material that's suspended in the atmosphere, dust and so forth, is interacts with the solar radiation. There's all kinds of complex atmospheric processes that go on. You've heard about the ozone layer and the ozone hole over Antarctica. So many of the processes in the atmosphere are dictated by localized differences in the composition of the atmosphere and the stratification of the atmosphere with altitude. Okay, so now I want to finish up on storms and tornadoes versus hurricanes. I've got a nice video that I'm going to play here, hopefully. There it goes.
What's the difference between a hurricane and a tornado? I'm structural meteorologist Jason Myers, and they are both a testament to Mother Nature's fury. They both spin counterclockwise in the northern hemisphere, and they both cause loss of life and property each and every year, but they are far from the same thing. For one, they both form in very different ways. Hurricanes form in warm ocean waters. Moisture evaporates, rises, and begins to circulate. As the storm grows, winds continue to speed up, and eventually an eye forms around the middle. Tornadoes, on the other hand, spawn from thunderstorms. Rotation in different layers of the atmosphere within a thunderstorm create a funnel cloud that eventually reaches the ground. But neither one of these is necessarily more superior than the other. Difficult to compare, but something we can compare: size. Hurricanes can be hundreds of miles in diameter. The biggest tornado ever recorded had a damage path of a little more than 2.5 miles, but most are only 300 to 400 yards. In fact, tornadoes have been known to spawn inside a hurricane. Advantage: hurricane. Now round two. What about wind speed? Hurricanes may be bigger, but tornadoes still pack a punch for their size. Hurricane force winds range from 74 miles an hour for a weak storm all the way up to 157 miles an hour or more for a catastrophic Category 5. A weak tornado starts out with winds around 40 miles an hour, but an EF5 tornado has winds anywhere between 261 to 318 miles an hour. Much stronger than the strongest hurricane force winds. Point: goes to tornadoes. Tie ball game. Next round. What does more damage? Tornadoes do all their damage using those extremely strong rotating winds. Hurricanes, however, come with a triple threat. They use strong winds, heavy rains, and storm surge, bringing huge waves crashing on shore, causing more flooding. But even so, tornado and hurricane activity can vary from year to year, but study after study has shown that on average, they're both equally damaging and deadly. This one is a draw. But what lasts longer, has the endurance, the staying power, the stamina? Hurricanes last for a few hours to a few weeks, and the average falls somewhere in between. Tornadoes are on the ground anywhere between a few seconds to maybe a few hours for an especially strong storm, but the average is somewhere between 2 and 15 minutes. Hurricanes can go the distance. Tornadoes and hurricanes vary on warning time as well. Since hurricanes take so long to form and do a lot of traveling before reaching land, people usually have plenty of notice to take cover or evacuate. Watches are typically issued 2 days ahead of time, and warnings are issued 36 hours before anything happens. Tornadoes are completely different. Watches are sometimes issued an hour or two ahead of time, and the average warning time for a tornado is 13 minutes. Just enough time to get to a safe place. Tornadoes are definitely scarier for this reason alone. And now we've ended up with a tie, so it's settled. Don't mess with either of these storms. Thanks for watching. Don't forget to like, comment below, and subscribe.
Okay, so that was a little bit fanciful view of tornadoes and storms. We're principally going to be talking about hurricanes when we consider storm effects, because they form over the ocean and they're so much related to interaction of the atmosphere and the ocean. So there's this energy implicit in storms. Now, the storms that he talked about were tropical cyclones, which occur typically in the northern hemisphere. We don't typically get hurricanes in the southern hemisphere, although recently there have been actual hurricanes forming and menacing the coast of Brazil and South America. That's an unusual weather pattern, and the reason for that is being debated by oceanographers and meteorologists. There are also storms, which similar cyclonic storms, which can form in the temperate and polar regions. These are called extratropical cyclones. And extratropical cyclones can meet up with other sorts of storms and form what they call superstorms. So an example, so this is the typical path of tropical cyclones forming in the North Atlantic, very seldom in the South Atlantic, but you do get South Pacific hurricanes and storm-like events called typhoons in the Pacific region, and typhoons can be equally powerful and destructive as hurricanes. Superstorm Dennis and Superstorm Sandy were examples of cyclones which formed due to cold air displacing warm air and creating the same upward motion. And superstorms which coincide with other storm events can create extremely damaging conditions. And we saw in the real-time data that I showed on Tuesday that there's actually an extratropical cyclone was present on Tuesday in the North Atlantic. So storms and the formation of storm events are a very important component of what can happen due to the interaction of the atmosphere and the ocean. A couple more topics that I want to talk about. One more topic in particular was the presence of monsoons, monsoonal patterns, because they have such an important impact on ecology, human activity, and agriculture. And monsoon, we're going to be thinking about monsoon, we have to get back to this concept of sea breezes and land breezes. And we talked about sea breezes and land breezes as being part of a sort of a diurnal 24-hour cycle, where sea breezes occur as warm air ascends and pulls cold air off, or cooler air off of the ocean. So warm air is rising and it's being displaced by the cooler air offshore, and that creates an onshore flow. This onshore flow can bring with it moisture, and this moisture can form clouds. The clouds can cause precipitation. The opposite occurs when the land cools off at night, and then the cooling air, and of course the land is going to cool off more rapidly than the ocean will, because the ocean mass tends to conserve heat. So with the cooling land breeze, you tend to have an offshore flow, and that tends to hold the water generated, or the water vapor in the clouds and the precipitation produced from the ocean in the offshore region. Okay, so this is a 24-hour sea breeze and land breeze cycle. Monsoons are an example of a sort of seasonal pattern in this process. And so monsoons, and this is a monsoon shown over Kathmandu in Nepal, and you can see the Sri Dagon pavilion here and the little flapping prayer flags. I've been in Nepal during the monsoon. I didn't take this video, but it's really impressive the way in which the rain just sort of comes down. So the monsoon rains are a feature of the Indian subcontinent. Well, what's going on in the monsoons? In the winter months, the land is cooler than the ocean, and so the air is denser, and that dense air displaces outward and tends to hold the evaporation and the storms offshore. So that's the condition in the winter months. In the winter months, the mountain regions in particular, the Himalayan mountains, are cooler, and that cold air tends to push offshore. So here's this ITCZ, the Intertropical Convergence Zone, and that's well south of the equator in winter months. What happens when the monsoons come is that the warm air starts to warm up the mountains and the land, and that warming trend creates a current, sort of a large-scale sea breeze. And so in India, and when spring leads into summer, and there's sort of terrible heat, and everybody is suffering and waiting, and then suddenly the monsoons start, and these heavy rains start falling. And we're kind of familiar with that living here in Florida, because during the summer months we don't have the sort of giant scale rain that we get that is present in actual monsoonal regions, but we do get that sort of monsoonal pattern of afternoon rain showers and intense downpour that result from moisture being transferred from the Gulf of Mexico in our case, and then falling out of rain as rain over the coastal regions. And so we do experience something very like a monsoonal pattern of heavy rainfall in the summer months, particularly in the afternoon. Okay, well, that was the material that I wanted to cover about Chapter 8. So we have this uneven heating, changes in variation in solar energy, as we make this annual rotation. The tilt of the Earth is the absolute forcing factor that causes seasonal or hemispherical differences in temperature and climate patterns, and all of that results in the motions of the atmosphere, as we've discussed. And we'll be getting back to that when we look at the ocean circulation next week, and then in the chapter and the readings that are assigned for next week. Are there any questions over the material that I've covered with atmospheric circulation? There's a lot of material. We've gone over it a bit fast, but I think that the principles that we've laid out should be pretty apparent to everyone, and that I don't see any reason why anybody would have a difficulty in grasping this. But are there any questions, anything that I can clarify?
I have a question.
Yes, Joseph.
So from the equator, it's Hadley cells, then convergence cells, and polar cells moving upwards?
Hadley cells, Ferrel cells, and then polar cells. Ferrel, F-E-R-R-A-L, Ferrel. Yeah. Same sort of pattern though, this sort of rotating bands. And those, the direction of surface winds, that's what, is deflected, so that in the Ferrel cells, the wind patterns are northward, whereas in the Hadley cells in the northern hemisphere, the general wind pattern is southward, and then the Coriolis effect the Coriolis effect is deflecting that pattern toward the west, toward the right, toward the west in the Hadley cells, and toward the east in the Ferrel cells. Okay.
Okay, thank you.
Any other questions? Anything at all? Okay, so now we're going to split into our different groups, and then Carrie and I will go around from group to group. We'll try to make it to everyone. We'll only be able to spend a little bit less than about 10 minutes or so with each group, but you should use this time to start thinking about the specific topics. So just going through, we've got tiger sharks who are working on ocean acidification. So obviously they need to think about the way in which the CO2 balance is generating or changing ocean acidity, and how that is changing in real time, and what some possible consequences of this. Hazardous material situations, so the danger zone, I haven't interviewed them, so they're perhaps thinking about oil spills or other sorts of pollution effects. The aquaholics are looking at climate change. So the ways in which, and that specifically relates to things that we're talking about now. So there's ocean winds. So how are ocean winds generated? Our ocean currents, tidal currents, which are potentially harnessed for energy generation. Oil spills, growing food and fuel in the future, living marine resources. So a number of the groups that really have got to do a little bit more work in developing the theme of their research. Dead zones, problem with overfishing, impacts of oyster fishing, oil spills, deep sea corals. So we've got a number of different topics here. And I hope that the sort of outline that I put forward in the first slide of today's lecture will give you a little guidance on thinking about the major topics that we've covered, and how you can take those principles and apply them to your research, not only understanding better what you're reading and what you're learning about, but then also communicating that in your report and in your presentation. Okay, so now I'm going to open up the breakout rooms. I'll stop the share, and I will open the breakout rooms, and then Carrie and I will go from room to room, and hopefully we'll make it around to all the rooms. If we don't, we're available, and we can schedule a special conference. So I'm going to open all the rooms. Please go in, and please use this time to work on the milestone 2. And we're going to be doing a similar thing on Tuesday. I've changed the due date for the milestone 2 assignment to Tuesday night. So you're going to have at least these 2 class periods to be able to work on it. Because on Tuesday next week, I'll give a brief lecture, somewhat as I did today, to introduce the concepts of ocean circulation. And then the more in-depth lecture will happen on Thursday. Okay? All right, so opening all rooms, and we'll be seeing you shortly in your rooms. Okay, let's see. Carrie, I need to get you participants.
I can get into any of them, it looks like.
You can?
Yes.
All right, great. All right, well, off you go then. I'll start at the top and you start at the bottom.
Sounds good.
Okay.
We could do corals, but then corals relates to so many other things. It's probably a good, like, broad thing to do.
Okay, so you guys, you're tiger sharks and you're working on ocean acidification. Have I got that right?
Yes.
Okay. Well, corals is great, but there's a lot of other concern about how ocean acidification is affecting the plankton. There are many varieties of plankton, coccolithophores and others, that make their shells, or what they call tests, but you can think of them as shells, out of calcium carbonate. And there's a great deal of evidence now beginning to accumulate that shows that the decrease in pH, the increasing acidity of the ocean, has started to interfere with the ability of these plankton to form shells in the larval stages. And then actually, when they've actually reached maturity, their shells start to erode. And there's accumulating evidence that that's could have an effect on plankton populations across the ocean. That's a huge concern. I mean, because roughly half of the oxygen that we get, that we breathe, comes from primary production in the oceans. And about a third to a half to 60% of the primary production can be attributed to organisms that have calcareous skeletons. And so, we're potentially impacting, something like the source of something like 25 to 30% of the oxygen that we breathe. So that's a really important topic. You could also, relate that to corals, but I think if you focused on that, you'll find a lot of really cutting edge research, and you'll have a chance also to highlight the real concerns that scientists have and that we should all have about ocean acidification and the causes of ocean acidification, which are unambiguously carbon dioxide. So one of the things that climate change skeptics, deniers, whatever you want to say, one of the things they say, well, CO2 is good, because plants use CO2 for, to make for primary production. So they make, everything that we eat is, ultimately made from, the CO2 that well, that's certainly true, but, the chemistry, the ocean chemistry is unambiguous. If you increase the CO2 content of the ocean, that CO2 is going to dissociate. The first dissociation product is carbonic acid. That carbonic acid lowers the pH, and that has this effect. You can also look at the different times in the past. And so paleoceanography tells us a lot about how the geologic history, the oceans had different acidities, different pH characteristics at different times in the past, and that during mass extinction events, the ocean acidity may have gotten extreme. There may have been extremely low pH values during mass extinction events, which would have led to whole scale loss of marine communities. Okay. I've thrown a lot at you, but if you follow me, so there, if you go and look at ocean acidification on the Web of Science, and then start looking for plankton effects, you'll find a lot of material. And if you do the process that I suggested of looking for recent papers, highly cited papers, review papers, that'll give you a guideline into that. And I'm also quite sure that I know that there is, a lot of material that's covered in the popular press and magazine articles that you'll be able to find to get better examples, nice pictures, discussions of what the impact of that could be. Okay? Does that make sense? Any questions? I'd like to move on to the next group, but I want to make sure you're on track.
Sounds good to me.
Okay, so as you do that, remember, you can go back and look at chapter 7 and understand, what the processes involved. And so you can introduce that and explain that in detail, and that will help the class and help you to understand this really important principle of how it works. Okay? All right. Good luck, and I look forward. We'll probably talk again on Tuesday, and you can tell me where you've gotten. Okay? All right.
Thank you.
Thank you.
Hi, Ashley. Do you need to join a room?
Yes, yeah, I'm so sorry. I lost my Wi-Fi connection, so I need to be in group 3.
You're in group 3. All right, let me see if I can.
Sorry about that.
No worries. Here you go.
Thank you.
You bet.
We can already start
Okay.
so,
I got it then.
write it down. Okay. So intro/body, we talk about the more general impacts of nuclear waste materials in marine environments. And then body paragraph 1, we go into depth, we go into details about specific events. Body paragraph 2, we compare those to like controlled experiments. And body paragraph 3, we talk about the control experiments in body paragraph 2. Body paragraph 3, we can do comparison, compare and contrast of the two, effects, bias, all of that stuff, and then like just conclude it all.
Yeah, I think there's also something that we could talk about that would be interested is we could talk about government regulations for controlled release of nuclear waste, and we can talk about whether or not those are actually like effective limits in terms of the ecological impact that they have. And I think that could be interesting to talk about too, whether or not they're actually high enough restrictions in order to prevent serious damage. So I think
like
that would be
with
interesting.
what you're talking about, Maya, maybe like our format can just be like a case study for like the body paragraphs, and we have like all these criteria, so like government regulations that were violated, like what Isabella was talking about, like comparison to the control, and then like we have like these certain criteria, like the principles that we talked about in class today, and then we do like a case study, like the 2 case studies, whether it's like Fukushima or like something else, and we just like have all these criteria that each case study hits in like the body paragraphs that Isabella was talking about.
Yes.
Hi, Danger Zone. Could I just interject a little bit here for a minute while I'm visiting you? So it sounds like hazardous materials, and you're going to focus specifically on nuclear hazardous materials. Wow, what a great idea! Because that means you can look at the why do we have nuclear power plants? Why are nuclear power plants located next to the ocean so often? Well, it's because of cooling water. They need to get a supply of cooling waters. And then, when you have Fukushima, when Fukushima occurs, why did Fukushima happen? Well, it was because of a horrible tsunami that resulted from a massive earthquake in this tectonically active region of the world. So there's a nice tie in there. And then, one of the horrible outcomes or consequences of Fukushima, it wasn't that they didn't know that there could be tsunamis there, but they built a retaining wall. But the retaining wall is like 22 feet high, and then the tidal surge that came over was like 33 feet high. So they knew it was coming, but they didn't know how bad. They didn't anticipate how bad it could be. And then they had all their pumps underground, so they flooded. It was a lot of bad planning and failure to anticipate what the ocean could do. But what I think is interesting, and where you can tie in some of the other principles of oceanography, is tracing the plume of radioactive material that has come out of Fukushima. And there's a lot of interesting oceanography there. First of all, how do they trace it? Well, they're looking for the radioactivity of ocean water, which is pretty minuscule actually, but it's still detectable. And so they can trace it as it goes across the Pacific Ocean. And so it tells us something about the direction of ocean currents, the speed of ocean currents, and the potential for that material, that radioactivity, to be distributed around the planet, around the ocean for certain, and potentially around, because I think that the prospects, I haven't checked lately, but Fukushima is an enduring problem. They have not fixed it. They're sort of got a temporary cap, but they have to actually freeze the ground to stop the water going in, and it's a huge expense. And so, that'll give you some, a lot of stuff. There's another example of this where there was a nuclear submarine. You'd have to look it up, but it was a nuclear submarine in Russia that had an accident and sank. And then, I guess it was the Soviet Union at the time, they denied that it was happening. But scientists noticed an increase in radioactivity, and they traced it back, and they kind of busted them, for having this event. So there's that. So there are many other examples where you can apply the principles of oceanography that we're learning to this impact there. Okay. Questions, other ideas? So have you started to do your research? Have you started to dig into Science Direct or Web of Science?
Yeah, we all before today's meeting kind of each had a task of finding 3 journals or books, sources that we can kind of look over and pick the best ones that'll correlate to how we want to set up our paper.
Okay, great. Well, that's the way to do it, is to divide and conquer, get everybody input, coming at it from different points of view. And, by all means, look into the popular literature, because there's a lot of debate now, as we think about how are we going to decarbonize our energy supply. One of the things that people talk about is, nuclear power, we should consider nuclear power. Well, that is an invitation to your group to also consider nuclear power and form an opinion that you can defend. Is it worth the risk? At what level? If it's not worth the risk right now, what kind of circumstances might make it worth a risk later on? So those kinds of things can give you the opportunity for some really thoughtful analysis and really delving into things where the answer isn't clear. I don't think there's anybody who'll say, oh, well, it's binary, we have to do it or we don't have to do it. It's like many other things that we encounter as we try to manage our planet in so much trouble that you have to come down with you have to come up with the best solution given a lot of extenuating circumstances. Okay, so is it clear what's required for the milestone 2 from the assignment? No. Mason shakes his head. What can I help?
I mean, it's clear, kind of. I just kind of wanted to get like what your opinion on what we actually needed, so that way we're not overworking or doing too much work, not doing too little,
Okay, well, you don't have to write the whole thing. You could write an abstract, and the abstract can be, just sort of a summary. You can extend it a little bit to sort of think about, how you're going to, because you're going to end up with a lot of material. There's a lot of literature out there. You're going to have to boil that down into, something that's practical, and you've got a team here, so you can actually work with a lot of different things, but somehow you have to take those different parts of the research and combine them into a cohesive story that makes sense. I like what Isabella, you're thinking carefully about the structure of how to write the stuff. That's good. That you have to do that at all levels, but you can in your abstract, in your summary, you can sort of like predict what the overall research paper is going to tell. But it doesn't have to be a final, it shouldn't be a final answer. You're sort of writing where you think you are now, where you think you're going to go, but you should be prepared to be surprised and to learn things that you didn't expect, or to have ideas that that you're holding now kind of contradicted, when you actually delve into the science and the facts. And that's.
So are you looking specifically for this milestone? Are you looking for like an example of like source?
Sorry, I can't quite hear you, Mason. Can you?
Sorry. So for this milestone, are you looking for sources and like a general outline, kind of abstract for? That's it.
Yeah, you can you should do your sources, and you should annotate your sources. So in your bibliography, you should have a couple of sentences that say, what you expect to get out of this article and how you expect that to apply to the project, the report that you're writing, the presentation that you're going to make. And then, I don't think you probably don't want to get too in detail at this point about, how it's all going to be structured, but make sure you think about who's going to be doing what and write that down. So that way everybody's kind of on record, you sort of commit, okay, I'm going to read these articles and this is what I'm going to focus. I'm going to focus on Fukushima. I'm going to look at, other examples, and, here's where, whatever each individual is going to do. So then you kind of like, it's good because it sort of does a couple things. It says, okay, I'm going to be responsible for these things, but I don't have to be responsible for everything, right? So, that's a good way to do it. If that makes sense, Mason.
Yeah, totally.
And
Okay.
I saw that there was I don't know if I read this correctly, like an outline for the PowerPoint presentation. What are we supposed to do there?
Oh, well, I would just like you to, think about, so you're going to have, when we do our class presentations, you're going to have about 15 minutes. And so you want to think about, so 15 minutes, the rule of thumb is 1 minute per slide. You got 6 people in the group here. I guess 6. Yeah, 6.
7.
7. Okay, so you're going to have to be pretty well synchronized about who's doing the presenting. Possibly not everybody presents, so some people can do more work getting the presentation ready and then let others present. That's something you can all decide internally. But just sort of think about how, what are the the real key components of a 15-minute presentation about your research project. Okay, what do you really need? So you really need to show that a nuclear power plant absolutely has to have cooling, for example. And so that's why, why is that? Well, it's because the control rods, if you don't, the control rods are taking heat out of this system, and unless you can, have some place to put that heat, it can overheat the core. Have you guys seen the Netflix series Chernobyl?
So good.
Okay, gotta watch it.
Very good.
Gotta watch it. It's an assignment. Do it this weekend. Well, I don't know if you want to binge it or not, but it's especially the first episode or the first 2 episodes are just, they take all of the tropes of the horror movie, where like, oh, there's a door, you don't want to open that door because something really, and they just sort of like make it real for what was happening. So you got to see that, and it'll also give you some ideas about what you're going to present.
Thank you.
All right, so I'm going to bail out here. Any questions quickly before I go?
I just had a quick question about Maya was doing some research and she found examples of like nuclear waste that's released in a controlled environment. Is that something that you think would be like relevant enough to really highlight in our paper?
Yeah, absolutely. One of the things that people have talked about is taking nuclear waste and putting it in subduction zones, for example. And what would happen? Well, it sounds like, oh, it would just disappear. In fact, it would not disappear. In fact, that radiation would be present in the oceans. But that's something that you could, research and find out about. It certainly would be, but you also need to come up with a title here. You haven't quite got a title yet, so work on that. Sounds like you're sort of saying, nuclear power and the oceans, hazards and possibilities, or something like that. That would be a title. So that's something you also have to work on, because I don't think you're quite there with your title yet. But it sounds like you have a real clear concept on where you're going. So, all right, does that make sense, Haley? All right.
Thank you.
Okay.
Thank you.
Thank you.
Thank you.
Thank you.
Hello. So this is the Aquaholics.
Hello. Hi, yes.
How you guys doing?
Good, how are you?
I'm well. End of the week. So you are doing combating, so you're doing ocean energy, right? That's what we talked
Yes, sir.
about. We conferred before. And so I suggested some approaches like that. Have you been able to follow that up with any looking at the literature or any of that? Have you gotten a little closer on that?
Yeah, so we right now we are actually going through like one of the sources you said, the BOEM, and kind of pulling like graphs and stuff from them. So that's what we kind of been focusing on now, because obviously the figures and graphs are a very big part of this project. So we were kind of getting that settled in for a milestone 2.
Okay. And combating climate change, and maybe the way, did you like work on your title a little bit so it was a little bit more sort of scientific and descriptive? Any ideas on that?
You mean edit the title?
Yeah, edit the title.
Okay. We can work on that.
Okay, why don't you work on that? I mean, I think you've selected a good topic, but you want to make you're trying to be like a scientific presentation here, and scientific presentations kind of avoid that. I don't want to call it emotionalism, but they avoid that sort of popular hook that that you try for if you're writing an article in the Atlantic or somewhere like that.
Okay, so make it more like formal.
Make it more formal, exactly. Okay. Make it more formal. So how many references have you nailed down so far?
So far, we have about 9,
Okay.
and we're going through them right now and kind of looking at what specifically we're going to get from each one of those sources.
Okay. Okay. And then, so you're going to need more than 9. You know, I'd like you to try to shoot for something in the 15 range for the peer review sources. But, you know, like I was saying in the little introduction, you know, you can talk about, and there's something maybe I didn't say and I should say, is that you can, if you're trying to like talk about a big principle, like, you know, onshore wind or tidal energy or something like that, and you want to explain, you know, give an explanation of the principle, you can cite the book. You can take an example out of the book to say, okay, you know, here's how a tidal barrage might work. And, you know, this is the principle that's involved, you know, is that we have locally high tides at certain places. And we know that, you know, historically that we would expect a big tidal flow. And then, you know, so what are the specific, you know, engineering considerations and, you know, ocean management kind of considerations for putting in a tidal generation plan. See what I'm saying? So, you know, if you do need to depend on principles and, you know, make specific reference to principles of oceanography, but you don't have to like find original sources for every one of those in the peer-reviewed literature. You can certainly cite the book and, you know, and to, you know, for these big concepts. Okay.
Okay. Thank you.
Yeah, and so, you know, the other parts of this are, you know, putting together a pretty detailed outline of, you know, who's going to do what, you know, and there's a lot of reasons for that. You know, for one thing, it sort of puts people on record, you know, okay, Zach is going to do such and so, Janelle is going to do such and so, and you kind of know what your job is, but you also know you're not responsible for everything, that you're going to work together. And that, you know, both puts you on record, but also lets you rely on the team for putting the whole thing together. Okay. And so, you know, do go through and decide what your tasks and your timeline are. How soon do you need to get this finished? Who's going to do what? And that way, I think it'll help you to stay on track. That's the idea here, is to, you know, to make a structure and make a schedule that's going to help you to do, you know, an excellent job. And we're going to be, you know, Carrie and I, you know, are going to be working with you to help you bring these things in and to help you apply these principles that we're learning. So they're not just concepts in a book, but they're concepts that you read about, understand, and are then finding very real world examples and then explaining to everybody else how they apply. And that, you know, that I think is the, you know, is the way we really learn things, you know, more than just for passing the exam, but for actually, you know, including us in our skill set as we go out into the professional world. How's that for inspiration? Okay, guys, anything else? So, you know, look on literature cited, you know, when you're going out and doing all these things, you know, somebody should be thinking about the graphics, because, you know, if you're doing engineering, there's a lot of graphics involved. You know, what does a tidal barrage look like? And, you know, where are some pictures of tidal barrages? You know, what are things that they've done? What is you know, what is the, you know, offshore wind energy like? You know, what is the, you know, if you in Germany and Denmark, the North Sea is dotted with giant wind turbines, and there's a whole culture that you know, of people that work offshore, and there's a Helgoland is an island that Germany owns. It's part of the, you know, of Germany, and there's a whole community that, you know, live in a hotel on Helgoland, and every day they get in a boat or a helicopter and they go off to these giant wind turbines offshore. And so there's a whole culture of people that are working on wind turbines that, you know, didn't exist 20 years ago. So, you know, and that's coming to the United States, you know, so in the coming decades, you know, right now, I don't know if anybody has been offshore and out in the Gulf of Mexico, but there are hundreds and hundreds of oil platforms. Well, that's going to change. Those oil platforms are going to, you know, in your lifetime be replaced with wind turbines in a lot of different places. And how that happens, how they get the energy ashore, you know, that's a real, you know, it's a real issue. It's a real topic for, you know, for ocean science and for understanding, you know, the role of effective ocean management in society. Okay, any other questions? I'm gonna bail out and go to a different class, but if anything comes up, by all means, email me and Carrie. Email both of us, so that way you'll get an answer from somebody for sure, and stay on track. And then we'll get back together on Tuesday and see where you're at. Okay?
Just one comment.
Sure, Charlotte.
I feel like from doing all this research, what I'm most worried about is just getting like lost in all the information, because there's so much and there's so many aspects of renewable energy in the ocean, especially like facing climate change. So I was just wondering if you have like a recommendation of what we should specifically focus on, because I'm getting lost in like looking for all the peer-reviewed articles. There's just so much.
Okay, well, remember to look for the review articles. That's a way to, to narrow down, and because if you get a review article, then somebody's already done a lot of that. They've thought about what's important and, so that's one way to organize it, one way to parse it down. And another way is to look for more recent material. What are the latest trends? And, another way to boil it down is, what is most likely to happen? So, we probably are not going to get ocean thermal energy conversion, building hundreds of plants of ocean thermal energy conversion. So you probably don't need to spend a lot of time, thinking about that. You can mention that it's something that's there, but that the real focus is probably going to be on offshore winds. So, I would establish the principles, why are there winds in certain areas, and how do we use those? How does a wind turbine work? What are the engineering challenges with wind turbines? And how would, so the principles of ocean science that apply to offshore wind turbines would also apply if we wanted to put turbines that would generate electricity from the Gulf Stream, for example, which other people have proposed. How could you apply the same thing? Does that help?
Yes, thank you.
Okay. Yeah, and so, look at what's most recent, look at what's most heavily cited, look for review articles, and that will help you boil it down. Because yeah, I sympathize. There's a huge body of material out there. But one of the challenges is to boil that down and pick out the ones that, that really tell the story, and that, give you a chance to show what you know about principles of oceanography. Okay? All right, folks, email me if you have any questions, and if you email, copy Carrie and me, and we'll get back to you.
Okay, thank you so much. Have a nice day.
Sure, you too.
Says what is important to them, they should talk about in this.
I write the abstract. I'll just wait to write the abstract until after we have somewhat of an outline.
Yeah, and your abstract and your outline, that's a really good tool for kind of focusing your work and sort of trying to, give it a little structure even while you're writing it, So you think, well, I can't write an abstract because we haven't written the paper yet. But a lot of times I'll write an abstract, when I have the data, if I'm writing a paper. And then I have to go back, of course, and revise the abstract to match what I've actually written. But a lot of times this helps me to think about what's probably coming. Okay. So you guys are doing, what am I? I'm in the oil spills, right? You're doing oil spills. So we talked before about the Deepwater Horizon oil spill and other spills, right? I think I did you earlier. Have you decided to narrow it down a little bit, or have you sort of narrowed your focus a little bit? Could that be reflected in your title? Because it looks like you don't have a title yet. Or Carrie, I asked Carrie to put together a list of all the titles for me, and she didn't have a title from you. So that's something you need to nail down, and it should be a formal title, not a sort of headline kind of title. So what's
we just came up with one.
Okay, good. What is it?
Impact of the Deepwater Horizon on marine life in the Gulf of Mexico.
Okay, so that's going to be your topic. Then you're going to focus on the Deepwater Horizon.
Mm-hmm.
That's not a bad choice at all. And you can reference, other oil spills, just for comparison to say, you know, how is the Deepwater Horizon oil spill different from other oil spills? You know, that can be you know, a way of highlighting the impacts that it had, and you know, creating some perspective there. Because, like, you know, for example, before Deepwater Horizon, probably the most notorious oil spill in U.S. history was the Exxon Valdez oil spill. You guys have probably heard of that, right? Well, that was a totally different oil spill. You know, it was a much smaller amount of oil. It was released, you know, in one event from a ship, you know, and, you know, after a couple of days, there was no more oil entering the water. And then it was happening in a completely different sort of ecological setting. In fact, there's a paper, which I will send you a copy of, called The Tale of Two Oil Spills. And that compares the Exxon. Anybody come across that? It's by Hazen.
I don't think so.
Hazen and somebody else. All right, well, I'll send you a copy of that, make a note to myself. And I'll send you a copy of that. And that'll help you a little bit. And the references in there are pretty good. And that, you know, when you start talking about the different ways that this oil spill impacted things, like, you know, that helps you to give it a perspective. You know, why was it? Because it was a deep water release, because it kept going. You know, the oil came out at 1,500 meters below the surface. You know, the release was, you know, huge, vastly greater. You know, the Exxon Valdez released somewhere between 10 and 20 million gallons, whereas the Deepwater Horizon was like, you know, I think 200 million gallons. So it was, you know, a lot bigger. And so, you know, that kind of perspective lets you then talk about, you know, the different impacts in terms of the context of the actual, you know, specific events that relate to that oil spill.
Who's the author for that paper?
Hang on a second, I'll tell you.
Because I may have found it. I just wanted to know so you don't have to go back and send it.
Let's see. Well, the second author is Hazen, but I can't remember the first author's name.
I may not have found it. You can just send it later then, never mind.
Yeah, I have to go into another, yeah, let me send it later. I have a copy. I totally have a copy, but I just, you know, I have a lot of papers, so I can't just lay hands on it right now, but I'll send it to you. And it's a nice review article, because it does talk about, you know, it gives you a broad overview of the Deepwater Horizon. Now, one topic that's going to come up in Deepwater Horizon, well, I'll send you my paper as well. Have you seen my paper on the surface oil, natural and unnatural oil slicks in the Gulf of Mexico? Did you come across that?
Did Carrie email that to us after like our meeting? Was that the one that she emailed us?
Well, it's not a bad article. It's a pretty good article, you know, because it talks about how the oil was distributed on the surface, and you know, it talks about dispersants and the way in which, you know, dispersants may have affected the way that oil was transported on the surface. And you know, dispersants are a big topic in all this. Now, you know, there's an example. You know, just sort of as an aside, you know, I thought that you know, one of the better ways of getting rid of oil was to burn it. And I think that, you know, I thought that burning oil, you know, had less of an impact than using dispersants. But it turns out that one of the things I hadn't thought about was all the smoke and the way in which that smoke, the soot particles in that smoke, could impact marine mammals and sea turtles. because, all that smoke goes up in the air, but the particles, don't drift around. A lot of the soot settles back on the ocean. And then when, marine mammals, porpoises, whales, come up to the surface to breathe, they eject their outgoing breath, and their ingoing breath is supersonic. There's a tremendous, power of air when they breathe out. So they come out and that's what makes the giant spout of the whale. Well, what that does is it, vaporizes anything that's floating on the surface of the ocean, and then it captures, when they inhale again, and it captures those soot particles. And so now there's emerging evidence that says that, the lungs of marine mammals were heavily damaged by these soot particles. And so that's something that I hadn't, really considered, when I was thinking about this. So, those are the kinds of things that you can find, and, the circumstances of the response directly relate to that. Okay. Okay, so your abstract, your outline. Now, the other thing that I'm suggesting to everybody, if I haven't already said it, is to, be pretty deliberate about your, tasks and timeline. So everybody, you're on a team, you got a lot of material to cover. It can be a little daunting, and particularly the Deepwater Horizon, because there's literally thousands and thousands of papers out there. It can be daunting. If you divide up and say, okay, I'm going to look at whales, I'm going to look at fish, I'm going to look at plankton, I'm going to look at birds, I'm going to think about, surface transport, I'm going to think about the deep water plume. If people take different topics, then, and bring, do the research on those materials, then, what you're on tap to do, what you've committed for, but you also know that you don't have to do everything, that you can get the material and bring it back, and then you can start digesting it. So that'll really help you to, to stay on track with all this. Okay, so, and that's also part of the assignment, is to write down who's going to do what. So that's to encourage you to go ahead and commit to things. And so the idea here is to, is to give you the chance to learn about, to take the things that we're looking at and, understand them well enough, and then apply them in this real world context. One other thing that I didn't mention in the general class was that if you have some particular principle that you'd like to talk about, the loop current, or, the seasonal weather patterns, or whatever, and, it's a big concept, you don't have to go out and find a peer-reviewed article on that specific thing. You can just cite the book or a similar textbook. So if you're, if you want to talk about some principle, for example, you need to talk about the way in which the ocean is structured, because at 1,500 meters, you have one sort of ocean structure. It's cold, it's dark, it's relatively unchanging. In the surface waters, you have a completely different regime, and you can talk about that, and talk about why that occurs, and cite the book, for structure of the water column. Okay, so you don't have to, that takes a little bit of the pressure off of, finding some specific article that somewhere in there mentions something about the thermocline, something like that. Okay.
Okay.
All right. Well, we'll talk again on Tuesday. We'll do the same thing. We'll have a brief lecture, and then we'll get back into our breakout rooms. And I'll look forward to hearing the progress that you made. And then, of course, the milestone 2 is due on Tuesday night. Okay.
Also, Professor, should we submit a revised version of our milestone 1 with like our added title and our added bibliography, like properly cited?
Yep.
Okay.
You get some points back if you do that.
All right. Thank you.
Thank you.
All right. Hi, Carrie. You're back.
Yeah, I had got an email from someone that couldn't get into Zoom. So I was saying if it was because no one was in here to let her in, but I think she's just having some sort of trouble I can't fix.
Okay, well, I've gotten through 4, so I got time, I guess, for 2 more if I hurry. Now, did you talk to Ronnie?
No, he wasn't there.
He wasn't there. Oh, okay, you checked.
Mm-hmm.
He wasn't there. Okay. Well, he's going to have trouble. He wanted to do this on his own, he might end up dropping. Anyway, we'll see.
Yeah,
Right.
I don't think he's, he wasn't in here last time we were in breakout rooms, so I guess on Tuesday either, so.
Oh, really? Well, he's probably going to drop that. Oh, well, who knows? All right, so I'm going to go to another room here. I've gotten through groups 1 through 4. How far did you get?
I got up to 7.
Up to 7. Okay, so if I do 5 and you do 6, we'll have the waterfront covered. And we got about, so if we do it for another 5 minutes, and then I'll bring everybody back together and we'll go. Okay.
Okay.
Here he is.
Here I am, laid back leatherbacks. What's up?
Hello.
Can I do some screen sharing to show you what we're working on?
Oh, sure. Great idea. I think you can do some screen sharing. Go ahead and see. Does it let you? Yeah, all right.
Cool.
Okay.
First question I had, I just wanted to make sure that we're supposed to be structuring this paper like a scientific paper, like with an information, material methods, data results, discussion stuff.
Yep. That's correct.
Fantastic.
Okay, well, let me give you some, it looks like your sort of history of the topic. Make sure in your introduction, the one thing I always want to see in an introduction is a statement of the scope and purpose of the paper. And, so that should say, somewhere at the end of this, you should say something like, this paper will consider aquaculture as a potential food source and examine the pros and cons of this topic, this means of food production, something like that. And then, but you're not going to be covering everything to do, so you need to sort of describe what the scope is, how we're going to talk about specific case studies, or we're going to look at examples in the developing world, or we want to look at things in the Gulf of Mexico, or we want to compare salmon farming in Norway to shrimp farming in Vietnam, whatever. I don't know what, I'm not don't know how you're exactly taking this, but those are some ways of sort of narrowing the scope and then telling the reader and the viewer where the paper is going. And that's a really important thing to do in the introduction. And so you can talk about why aquaculture has increasing importance. I mean, if you go to McDonald's, if you eat shrimp, at a restaurant, it's almost certain that shrimp comes from Vietnam, Nicaragua. There's just a few places where they're raising shrimp. So all the shrimp that you eat, when you go out to eat shrimp, back in the day when we could actually go out and eat, that shrimp comes from aquaculture. Well, the shrimp culture is hugely impactful. There are lots of environmental impacts of shrimp culture. Loss of mangrove, shrimp ponds, once they set them up, they don't last for very long. After a couple of years, the accumulation of waste material and makes the pond toxic. So the yields fall off. So there are lots of issues with that. Okay, so that's but that would be something that you could bring out in your so we want to contrast and you're better off a lot of times if you have a few clear examples rather than trying to cover everything. You can make a brief statement about maybe give some statistics. So in an introduction, for example, you might say here's the trend of fish production or food production from aquaculture over the past 20 years, whatever it is, and we can see that it's increasing. This is important because overfishing in the ocean, XYZ. And to discuss this, we're going to take 3 specific examples. We're going to look at shrimp farming, salmon culture, and catfish farming in Mississippi, or whatever it is, and then talk about what you can learn from using each of these examples and what that's going to tell you about the larger topic of aquaculture. Okay. All right, well, sounds like you're on track, and I want to say, I'm going to close all the breakout rooms now. We'll get together briefly before the end of class. But if you have any questions, anything comes up, anything specifically I can answer before we go, anything you're running into?
Would the wait, so for those like topics we put next to introduction, materials and methods, like those all look good, like they look like that they would be like relevant for that?
Yeah, I mean the methods and material, yes. And if you're going to focus on a couple of different types, then you could, in your methods and materials and methods, you could focus specifically on that. You can also say something about, where you found your sources of information and how you chose those. And you might say something about, popular perception of aquaculture. Okay, discussion and conclusions. So yeah, breeding and harvesting of plants. So having to understand primary production, waste disposal, nutrient loading, eutrophication, lots of topics come up there. But you also have to consider, what are the circumstances, climatic and oceanographic, that create different opportunities for aquaculture in different parts of the world. So those are sorts of, big principles that you can apply. Does that help, Joshua?
Yeah. Wait, so you're saying like, I'm the one doing materials and methods, which is why I'm asking this.
Sure.
You're saying, you're saying as well as this, like what's already written there, like how it works and the different types, you're saying I should talk about like discussion of like where we found our sources? Like I haven't written like a paper like this before, like since I'm a sophomore, so.
Okay.
Yeah.
Well, it's not where you find your sources so much as how you chose the sources or what your different sources, tell you about the overall topic. So, we, in researching this paper, we found peer-reviewed papers that discussed, the nutritional needs of salmon. We also, so you might want to just, I don't want to overemphasize that, but you might, be aware that that's part of your overall, because those are the materials that you're using, right? Your materials are the source that you got. So you want to, give some kind of a nod to that component.
Like credibility to the sources.
Credibility is another thing. Yeah, right.
Okay, but also the stuff that's also there, like I should talk about that too. Like that should be part of that same section.
Right. What are the technologies? Cage culture, pond culture. That sort of thing. Those are the methodologies that are used. How do we, what are the sort of, measurement and monitoring techniques that you use to try to, that aquaculture practitioners have to use to measure their productivity. So how do they keep track of, the toxicity of the pool? What sort of things are they paying attention to? What are the nutritional requirements for the different aquaculture species? Those are big issues. Okay, I gotta bail out here because I'm gonna close all the breakout rooms and okay, any questions before we go? We got a few guys. We're just at the end of class, so if there's anything that's come up, let me know. Nothing?
Nope.
Okay, well, all right. So you guys got some work to do over the weekend, and I'll look forward to seeing your progress when we get back on Tuesday. So any questions, anything come up for anyone? I didn't get to talk to everyone, but I think we managed to get through all the groups. And hopefully you've got some guidelines there. So, and if we're going to give you some points back, if you revise your title. So some of the groups that needed to get a title, go ahead and revise that title, send it in to Carrie and to me, and we'll give you some points back on your milestone 1 score. Okay, well, looks like we're at the end of the class, and so I will thank you all for being here once again, and look forward to seeing you again on Tuesday. We'll do the same thing. I'll have a more brief lecture on Tuesday, introducing the topic of ocean circulation. Then we'll go into breakout rooms, so make sure everybody's on track for their milestone 2 submission. And then there'll be a more in-depth lecture on Thursday. Sound good? Okay, everybody. See you later.
Thank you.
Bye.